Thank you, Philip. Thank you for inviting me to present at the symposium. I will talk about architectural explorations in the age of robotic building. My name is Henriette Bier. I am associate professor at the Technical University Delft. And I'm leader of the group, robotic building group, which was established within Hyperbody 2014, and since last year is part of architectural engineering. So the focus of our work is on robotic systems integrated into the physically built environment and building processes. This exploration we implement by means of design-to-robotic production, assembly, and operation. So the following slides are going to try to explain what that means. So the first project we developed in 2014 when we also established the robotic lab, and it has been exhibited at Centre Pompidou. We usually start with an overall design, in this case a pavilion, and this digital model has been transferred into a robotic path, in this case using light. In this process, basically the students learn this process of digital, physical, and then moving towards 3D printing robotically using ceramic clay in this case, and on a double curved surface. But usually in all our projects, we aim to prototype a fragment one-to-one. So we took a fragment, we structurally optimized it to generate a porous pattern. So this porous pattern was supposed to minimize the use of material, and at the same time, the aim was actually to at one point achieve robotic path optimization. As you can see here, the cells are separate, while you want actually to have a continuous path, which we achieved in the next step with this one-to-one prototype that was in the end exhibited at, or the process was exhibited at Centre Pompidou. And here you see again the optimization routine. And this was basically the start of a process where we engaged in looking into compliant systems. In this case, we developed compliant chaise longue with variable stiffness. Again, we used structural optimization routines, but also we developed the cellular structure, which at the moment is in process of being patented. And here you see a short movie presenting this project. It has been implemented with industrial partners, and we had funding from national funding. And we explored the design with the usual, let's say, design, parametric design computational tools. And we designed this pattern in such a way that has different stiffness, variable stiffness, depending on the behavior that we wanted. So as you see, the cells are varying. And here you see the 3D printing process with the system that the industry partner offered to use. And here's the printing process. It took about 30 hours in one go, including troubleshooting. And here you see the test. So basically the back is more flexible than the rest of the structure. And this behavior was basically the main interest for us in this case. In general, we look into additive and subtractive techniques, and we, again, using subtractive techniques, we explored flexibility with a material that is not flexible, in this case EPS, And the final prototype, the use in this case was actually acoustic optimization. So we wanted to have this flexible behavior in order to achieve acoustic optimization. And here you see basically the simulation on the existing overall shape. And the results were mapped on this overall geometry and were actually overlaid with the structural optimization. And this was basically the fragment of the prototype that we then one-to-one produced. The brown material is cork, the white is EPS. The white material is structural, while the cork, which is flexible, addresses acoustic requirements. Oops. So this was the one-to-one prototype. And just to get an idea of the overall design, this was actually designed for a stage that was supposed to be built for the Symposium. And the cork is used for the seating area, but here you see basically the parts that were mapped to address the acoustic requirements. So in addition to these experiments, we look into integrating sensor actuators into the built environment and what we call design-to-robotic operation. And some of the projects that we develop with students are involving, in this case, use of air, pneumatic, this is pneumatic structure that changes shape, so it's a mattress basically floating on the river of Rotterdam, and which curls up when people take a break and want to have some protection from the strong winds that we have there. In addition, we looked into local empty office spaces in Netherlands and also into reconfigurable apartments. And the students were asked actually to design a reconfigurable system for an apartment. And as always, we ask actually the students to not only engage in designing, but also find ways of materializing their designs and test their ideas. Usually the budgets are very low, so also in this case, the material that we use actually was much thinner than it was supposed to be. But still, we were able actually to prototype and test these ideas. Usually students work in groups, and they find actually this prototyping phase, design to prototyping phase, quite exciting. Amongst other, testing is something that is part of it. And this is the testing. So it holds for a while. Last, I'm going to talk a little bit about design-to-robotic assembly. This was a project that we implemented at Dessau Institute of Architecture, where we were involved about 2 years. And here you see the stacking, actually, of a geometry that was generated using linear elements of different sizes. And one of the challenges was also basically to stack in such a way that the elements are stable at all times, although, so to say, this structure had overhanging parts. And again, this was implemented with students from Dessau Institute of Architecture. Here you see the fragment showcasing some double curved surfaces. So I will conclude with a statement. And the statement is that what we are looking into in the next step is human-robot collaboration. Thank you very much.
So one question about the part about acoustic optimization. In which way did the process that you described exactly contribute to acoustic optimization in a way that other processes couldn't?
Well, the point is, of course, we would have needed to test. So we came up with an assumption. We went through a certain design-to-robotic production routine, but we did not test it. So in the end, I cannot tell you for sure that our assumption that basically this flexible material would really operate the way we want it. And this is actually something that we definitely need to look more into the future, in the sense that how we test our prototypes and ensure that the assumptions are indeed well. With the flexible chaise longue, we tested it, but not with the acoustic prototype.
Okay, so it was still, let's say, conceptual. In that sense.
Exactly.
Okay. Yeah.
Thank you for your presentation. You have really interesting and amazing projects. What I was wondering was regarding your experience with the robots now. Could you say, as I see, you have a pretty linear process in a way where you actually optimize and simulate things computationally, and then you give it further to the robot. So do you have any feedback loops where you actually can inform from the robot and go back to the
Thank you. Thank you for the question. Not yet. But there are actually experiments also at Bartlett where this feedback loop is established. So I do think that this is the next step to take.
Thank you.
Thank you.